Friends, let us pass on to the third chapter of our course in discrete mathematics. For convenience, we split this chapter into two sessions. The first one includes a detailed discussion of various counting techniques leading to the permutations and combinations. Many problems also will be discussed. We reserve the elements of the discrete probability theory to the next session. Counting is a natural process which all of us need in various real life situations. Occasionally, we find it difficult to answer the questions like how many or how often, etc. related to counting. One way to find answer to such questions is by actually counting. But this may be laborious and so may not be a wise step. The other way is to establish certain scientific methods to count. In this context, there are two fundamental principles which provide us with methods of counting by not actually counting. Our discussion leads to permutations and combinations. These were having more a fancy nature in the beginning, but when computers came into use, even for solving mathematical problems, these techniques grew to a higher level of application beyond its original fancy form. Fundamental principles of counting. There are two fundamental principles of counting. They are also known as the rules of sum and product. Suppose that a job termed as job 1 can be done in m different ways and another job termed as job 2 can be done in n different ways. Then first principle of counting says that both the jobs job 1 and job 2 can be done in m into n different ways. Second principle of counting says that one of the jobs job 1 or job 2 can be done in m plus n different ways. These principles can be extended to any number of jobs. These two principles are illustrated with simple examples. Assume that a boy has 5 trousers and 7 shirts. The number of different ways of his dressings is 5 into 7 equals 35. In case he has 5 t-shirts and 7 shirts, then the number of different ways of wearing them is only 5 plus 7 equals 12. A special type of continued product named factorial of a natural number is introduced in this context. For a natural number n, the factorial denoted by n factorial is n factorial equals n into n minus 1 into n minus 2 into etc. into 2 into 1. The factorials of the first 7 natural numbers are 1 factorial equals 1, 2 factorial equals 2, 3 factorial equals 6, 4 factorial equals 24, 5 factorial equals 120, 6 factorial equals 720, 7 factorial equals 5040. It is clear that n factorial equals n into n minus 1 factorial. Putting n equal to 1, the equation becomes 1 factorial equals 1 into 0 factorial. Even though factorials are defined only for natural numbers, we are forced to accept the value of 0 factorial as 1. Permutations. Consider the case where 10 boys are to be seated on 4 chairs in a row. Any one of the 10 can be seated on the first chair, any one of the remaining 9 can be seated on the second chair, any one of the now remaining 8 can be seated on the third chair, and any of the now remaining 7 can be seated on the fourth chair. Thus, by a repeated use of the first principle of counting, the number of ways of seating them will be 10 into 9 into 8 into 7 equals 5040. When we try to get this answer using the given two numbers 10 and 4, we can have it as 5040 equals 10 into 9 into 8 into 7 equals 10 factorial by 10 minus 4 factorial. Permutations or arrangements. The number of permutations of n items taken r at a time is npr or pnr equals n into n minus 1 into n minus 2 into etc. into n minus r plus 1 equals n factorial by n minus r factorial. It is clear from the definition that NPN equals n factorial. Also, in the definition of NPR, it is assumed that the items do not repeat and they are all distinguishable. So, to find the number of permutations where the items may repeat or the items need not be distinguishable, the above formula is inadequate. The fundamental principles of counting are directly useful in such situations. Permutation of indistinguishable items. If there are m items of the first kind, n items of the second kind, p items of the third kind, etc., then the total number of arrangements of all these items is m plus n plus p plus etc. factorial by m factorial into n factorial into p factorial, etc. Permutation of items that can repeat. If there are n distinguishable items which are to be arranged at r places where repetition of items is permitted, then the number of permutations is n raised to r. Circular permutation. When items are to be arranged around a circle, the situation is slightly different from that along a line. In a linear arrangement, there are two positions at the ends, but these two positions are fused together in a circular arrangement. So, certain arrangements which are different in a linear arrangement coincide in a circular arrangement. If there are n items, then each linear arrangement repeats n times, making the same circular arrangement. So, the actual number of circular arrangements of n items will be n minus 1 factorial. The circular permutation itself consists of two types. If the clockwise and anti-clockwise arrangements are different, then the total number becomes n minus 1 factorial. This happens when people are arranged around a table. If the clockwise and anti-clockwise arrangements are the same, then the total number becomes half into n minus 1 factorial. This happens when a bracelet is formed using beads or when a garland is formed using flowers. Example, the number of different words which may or may not have meaning formed using letters of the word article is 7p7 equals 7 factorial equals 5040. Example for permutation in which certain items are not distinguishable. Consider the word assassination. There are 13 letters consisting of 3 A's, 4 S, 2 I's, 2 N's, 1 each of T and O. Any change in the order of the 3 A's among themselves cannot be noticed. Similarly, for the other repeating letters also. Thus, from the total number of words, the number of repetitions due to the 3 A's must be divided to get the actual number of different words. Similar arguments can be made for the other repeating letters also. Thus, the actual number of words will be 13 factorial by 3 factorial into 4 factorial into 2 factorial into 2 factorial equals 1 crore 8 lakh 10,800. Consider the situation where 4 examinations are to be scheduled in a week so that no 2 examinations are conducted on the same day. The first examination can be scheduled on any one of the 6 days, the second on any one of the remaining 5 days, the third on any one of the remaining 4 days, and the fourth on any one of the remaining 3 days. Thus, the total number of schedules is 6 into 5 into 4 into 3 equals 6p4 equals 360. Example for permutation in which certain items may repeat. Consider the digits 2, 3, 4, 5 and 6. If we form the 3-digit numbers, then 222 is a valid number. That is, a repetition of items is permitted. As the digits at units place, any one of the 5 may be considered. Similarly, at the tens and hundreds places. Thus, the total number of numbers is 5 into 5 into 5 equals 5 raised to 3 equals 125. If 5 boys are given chess numbers, the digits 2, 3, 4, 5 and 6 and are asked to stand in a line, then it is not possible to read the number 222. The reason is very simple. A repetition of items is not permitted in this case. Example: consider the situation where one posts 5 letters in 4 letter boxes. Each letter may be posted in 4 different ways, and so the total number of ways of postings is 4 into 4 into 4 into 4 into 4 equals 4 raised to 5 equals 1024. Next example: consider the situation where 6 boys are to be seated in a line so that the boys A and B are always together, C and D are always at the end seats. The arrangement of C and D can be done in 2p2 equals 2 ways. The remaining 4 boys are now treated as follows: the boys A and B together as a unit and the remaining 2 as 2 units, so that altogether there are 3 units. These 3 units are arranged in 3p3 equals 6 ways. In each such arrangement, A and B among themselves are arranged in 2p2 equals 2 ways. Thus, the total number of seating arrangements is 2 into 6 into 2 equals 24. Example: suppose that codes are formed with 3 alphabets followed by 2 decimal digits. If both upper and lowercase letters are used, then the alphabet part can be made in 52p3 equals 1,32,600 ways. The numeral part can be made in 10p2 equals 90 ways. So, the total number of ways of forming codes is 1,32,600 into 90 equals 1,19,34,000. Combinations. Let there be 3 friends A, B and C. What will be the maximum number of greeting cards they send to one another during a new year? Clearly, each one of them can be a sender. Once a sender is fixed, there are only 2 receivers. Thus, the number of cards will be 3 into 2 equals 6. Now, let us find the number of handshakes when they meet together. Of course, the number of cards will be more than the number of handshakes. Each pair of friends acting the roles of sender and receiver will constitute one and only one handshake. Thus, there are only 3 handshakes. In other words, the number of greeting cards is related with permutations. When we find the number of handshakes, the different arrangements of the 2 friends involving the roles of sender and receiver need not have to be considered different. Thus, 2 factorial is to be divided from 3p2. Thus, the number of handshakes is 3p2 by 2 factorial. This discussion leads to the following definition. Combinations or selections. The number of combinations of n items taken r at a time is NCR or CNR equals NPR by r factorial equals n factorial by r factorial into n minus r factorial. From the definition, it is clear that NCR equals NC n minus r. This is expected since in practice, a selection of a few and discarding the remaining are the same. Example: if 23C2R equals 23CR plus 2, then there are 2 possibilities. Either 2R equals R plus 2 with R equals 2, or 2R plus R plus 2 equals 23 with R equals 7. Next example, consider the situation where 12 different toys to be put into 4 packets, each packet containing 3 toys. First 3 toys are taken out of 12 in 12C3 ways. Then from the remaining 9, 3 are taken in 9C3 ways. Now from the remaining 6, 3 are taken in 6C3 ways, which automatically makes the last packet of 3 toys. Thus, the total number of ways the 4 packets are made ready is 12C3 into 9C3 into 6C3 equals 12 factorial by 3 factorial into 9 factorial into 9 factorial by 3 factorial into 6 factorial into 6 factorial by 3 factorial into 3 factorial equals 12 factorial by 3 factorial raised to 4. In combinations also, if the items are indistinguishable or if the items can repeat, appropriate adjustments are to be made in the calculation. Example, 3 programs are to be scheduled in a week. If there is no restrictions on the number of programs per day, then effectively it is a selection of 3 days from 7 where repetition of days is possible. This can be done in 7 plus 3 minus 1 C3 equals 9 C3 equals 84 ways. In general, it can be seen that the number of different selections of n items taken r at a time with repetition of items permitted is n plus r minus 1 Cr. Example, suppose there are 3 apples, 4 oranges and 5 mangoes. Then the number of ways of selection of fruits will be 4 into 5 into 6 equals 120. Here, apples can be selected in 4 ways as no apples or 1 apple or 2 apples or 3 apples. Similar arguments are made for the other fruits also. Example, suppose the number of different divisors of 10,800 is to be found out. First, the number is written as 10,800 equals 2 raised to 4 into 3 cube into 5 square as a product of prime numbers. Any selection which may include none also of these primes and their product would give a divisor of 10,800. From the multi-set, set of all elements 2, 2, 2, 2, 3, 3, 3, 5, 5, any selection can produce a factor. This can be done in 5 into 4 into 3 equals 60 ways. So there are 60 different divisors for the number 10,800. After a study of permutations and combinations, it is natural to ask the following question. If all the permutations or combinations are to be written, then what must be the order? In other words, is there any order in which the different permutations or combinations are to be considered? We make it clear with one example. Suppose there are 3 statements whose truth values are true or false. The truth values may be 1 or 0 also. When we prepare a truth table, their truth values are usually written in the following order. P false, Q false, R false means the value is 0, 0, 0. P false, Q false, R true means the value is 0, 0, 1. P false, Q true, R false means the value is 0, 1, 0. P false, Q true, R true means the value is 0, 1, 1. P true, Q false, R false means the value is 1, 0, 0. P true, Q false, R true means the value is 1, 0, 1. P true, Q true, R false means the value is 1, 1, 0. P true, Q true, R true means the value is 1, 1, 1. This means that the different arrangements of the binary digits at 3 places has an order as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. It can be the exact opposite order also. Here in this order, the digits represent binary numbers written in the increasing order of their values. We can call it a lexicographic order or dictionary order. Now, how do we specify this order in the general situation? Suppose a permutation A1, A2, A3, etc. An is given. Our concern is what will be the next permutation? We can make use of the following guideline. The next permutation B1, B2, B3, etc. Bn must satisfy the conditions. First, Ai less than or equal to Bi, 1 less than or equal to I less than or equal to m minus 1 and Am less than Bm for the largest possible m. Next, Bm is the smallest element among Am plus 1, Am plus 2, etc. An that is larger than Am. Last, Bm plus 1 less than Bm plus 2 less than etc. less than Bn. We illustrate this rule with an example. Consider the different permutations of the 4 digits 1, 2, 3 and 4 to form 4-digit numbers in which the digits do not repeat. To start with, let us take A1, A2, A3, A4 as 1, 2, 3, 4. The next item 1, 2, 4, 3 is B1, B2, B3, B4. The first two places are equal. So, M equals 3 makes AI less than or equal to BI, 1 less than or equal to I less than or equal to M minus 1 and A3 less than B3. The condition Bm plus 1 less than Bm plus 2 less than etc. less than Bn cannot be checked here as the maximum value of indices is 4. There are 24 different numbers by the theory of permutations. When we use the lexicographic order to write them, it will be 1, 2, 3, 4, 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, 2, 2, 1, 3, 4, 2, 1, 4, 3, 2, 3, 1, 4, 2, 3, 4, 1, 2, 4, 1, 3, 2, 4, 3, 1, 3, 1, 2, 4, 3, 1, 4, 2, 3, 2, 1, 4, 3, 2, 4, 1, 3, 4, 1, 2, 3, 4, 2, 1, 4, 1, 2, 3, 4, 1, 3, 2, 4, 2, 1, 3, 4, 2, 3, 1, 4, 3, 1, 2 and 4, 3, 2, 1. Let's remind what we have studied in this session. A detailed discussion of the different methods of counting was made in this session. It was an attempt to prove that counting is not at all a fancy game, but it is a scientific process. The following questions are provided for you to practice. First, find the number of odd natural numbers having 4 digits formed using the digits 0, 1, 2, 3, 5, 6 and 7. Next, find the number of different words that may or may not have meaning can be formed using letters of the word mathematics. Next, find the number of different words formed using letters of the word mathematics in which the vowels occupy the same position as they are in the word. Next, as symbols there are 3 zeros, 4 ones and 2 dots. How many different codes of length 4 can be formed using these symbols so that no symbol is omitted? Next, in how many ways can 15 books, all different, be distributed equally among 3 students? Next, when 5 boys and 3 girls are seated around a table, in how many arrangements will no 2 girls sit together? The following books are recommended as reference. The Elements of Discrete Mathematics by C. L. Liu, Tata McGraw-Hill Publishing Company, 2nd edition. Discrete Mathematics for Computer Scientists and Engineers, 2nd edition by Joe Elmoth, Abraham Candle, Theodore P. Baker, Prentice Hall India Private Limited. Hope you have followed this session. We will continue our discussion with discrete probability in the next session. Till then, goodbye.